now this is for the first one was for the conduction. Now this is for the convection. Now for the convection, we have this formula. If I zoom that one in, so for the convection, we have this formula. R convection equals 1 over H AS, where AS is the area and H is the convection constant. Now in the case, imagine we got the surface temperature, which is Ts, which is the hot temperature, and this is, let's say, T infinity, which is the low temperature. If the rate of the convection is so fast, then the Ts will become equal to T infinity. Why is that so? Imagine the temperature Ts is 50 degree, and the outside temperature T infinity is, let's say, is another temperature. So what will actually happen is, if the rate is conduction is so fast, this temperature is 50, yeah, and that temperature is, let's say, is 20. In no time it will achieve this temperature, so the temperature will be achieved super quickly in no time. Hence the rate of the conduction or convection is extremely fast. Here H is the convection constant, uh, uh, convection constant, yeah. Okay, now let's have a look at that one. In case if that's a radiation, if we are having a radiation, so for radiation we use another constant which is known as H of the radiation. So R, resistivity of the radiation, is equal to 1 over H radiation and the surface area. For for the radiation, if we are looking for rate of heat flow, for the rate of heat flow because of radiation is given by this formula: temperature Ts of the body minus temperature of the surrounding TSURR divided by the R radiation coefficient or resistivity of radiation. This is also given by this equation. If you got a constant of radiation and the area of the surface, you multiply that with the difference between the temperature of the body minus temperature of the surrounding. That will give you the answer as well. The other equation is given by, which is a little bit more complicated, is given by the Ts to the power 4 minus T surrounding to the power 4 area. Now then we got two more coefficients. Now these two more coefficients depend on the permittivity, which is how much you are allowing the heat to permit to pass, and another property which we'll discuss later. If I got these equation, if I got the value of the Q, and usually this is the equation we use, if I highlight the equation, that one, this one, or that one. Out of these, one variable is kind of missing, and you can find that variable. Yeah. So you can rearrange that equation. If I rearrange the equation, I got the Q equals H AS and Ts minus T surrounding. Now I want to find out the H if I got all the values, so I can make the H the subject. This whole thing I'm multiplying, I can move on the other side. Q dot AS and delta T, which is Ts minus T surrounding. So that's how we find the value of the H. If we want to find the area, it's going to be area of the wall, Q dot H and the delta T, which is Ts minus T surrounding. Yep, that's how it works. Okay. You can actually see that's the area of the surrounding, which is that area of the wall, which is that's the temperature of that wall. This is the H, which is the coefficient, and that's the temperature. Now when we measure the temperature coefficient or the conductivity coefficient or the resistivity coefficient, um, all the calculation we do in thermodynamic is in Kelvin. We can have the we can have only, we can any other like Fahrenheit or let's say Celsius, if we can use that one, if it's a delta T, because if the temperature is 10 degree and the final temperature is 100 degree, the change in temperature is 90. Even if you convert that into Kelvin, the change in temperature will still be 90. Yeah, because you're adding 273 on the other side and 273 on the other side. But when you subtract, it will be 90. But everything else, we prefer to use the Kelvin scale, which is known as absolute scale. What will happen if we got a case where there are two different ways of heat transfer happening? So initially, let's say the body heat is being transferred to conduction, and then there is a gap. There is a gap between the walls. So then it's a convection, and then it's again conduction. So conduction, convection, conduction, and so on. So how do we find the total H, the coefficient? Now the combined H, the combined H, the coefficient is given by the H for the convection, H for the radiation, plus H for, if we got the H, or K, plus the K for the conduction. Conduction we use K. H is for convection and for the radiation. So where H combined is a combined heat transfer coefficient because of convection and because of radiation. Now let's move on to the next one. Now let's say we got a wall and we got a temperature here. I'm just calling it T infinity 1, and this temperature is T1, where T infinity 1 should be higher than the T1. The temperature of this room is a lot higher than temperature of that glass. So as the air comes touch the glass, because the glass, imagine it's, or the wall, it's also linked to the outside, so that temperature is a lot going to be lower. So there is temperature drop that can be like 40 and that can be 37. Now then we got a wall of certain thickness. Yeah, let's call L the thickness of the wall. The inside temperature of the wall is T1. We make an assumption that the temperature, the conductivity constant of the wall is uniform. Hence, the gradient will be uniform. And then we got T2, where T2 is the outer temperature of the wall. Outer temperature of the wall, if I write down values, let's imagine this is 40 degree. That might be 38 degree. That might be 28 degree, let's say, and this one is, let's say, 20 degree or 26 degree. Yeah, so it's going to be like that kind of thing. This is just an approximation. Now if I want to find out, if I want to use the same analogy here in this part, convection is happening, then in this wall there is conduction is happening, then in this side convection is happening again. So what I need to do is I need to find out the conductivity because of convection, conductivity because of conduction, conductivity because of convection again, and then I need to add them up. And this is what they have actually shown here. But if you have a look here, I assume R convection is happening from this stage T alpha 1 to infinity 1 to T1, and from T1 to T2 is the R of the wall, and then convection again is happening from T2 to T infinity 2. So we can write that in this formula, because the initial temperature is that and the final temperature is that. So I can do the difference. T infinity 1 minus T infinity 2 and divided by all the resistivity. R convection plus R wall plus R convection. R convection 1 is the inside convection. R convection 2 is the outside convection. Now we have the wall of a thickness L. Let's assume we got a wall of the thickness L. The area of the wall is A. The thermal conductivity of the wall is K. And it's exposed to convection on both sides, the inside and the outside. Yeah. And we know the temperature inside is T alpha 1 and the temperature outside is T alpha 2. And the heat transfer coefficient for inside wall is H1, for outside wall is H2, the convection inside and the convection outside. We need to make an assumption that T alpha 1 is a lot bigger than T alpha, when I say alpha infinity, T infinity 1 is a lot bigger than T infinity 2. Otherwise, the heat is not going to flow from inside to outside. It will be other way around. Okay. So when we discuss the rate, of heat convection, it's going to be into the wall is H1 area multiplied by change in temperature inside T alpha, T infinity 1 minus T1, which should be same because it's a same line, which should be the same as rate of heat conduction through the wall. Heat conduction through the wall, rather using H, I am going to use the K because K is the constant. Ka over L, T1 minus T2. Then after that, this is outside of the wall. So this one is outside of the wall. This is the wall itself. And this is inside of the in the room. Yeah. So outside is same H2, A area, T2 minus T infinity 2. Now I can bring this thing down. HA, I can just call it 1 over H1A1. I can bring that one Ka down as well, L over Ka, and this one 1 over H2A. Now remember, 1 over H1A is R convection. So I can replace this whole thing with the R convection 1, and I can replace this whole thing with R convection 2, and this one I can replace with the R of a wall, because R of a wall is L over Ka, and R of a convection 1 or 2 is 1 over H1A or H2A. Okay. Now I can add them. When you add the resistivity, you can find the total resistivity. In that case, the total resistivity is going to be R convection 1, R of the wall, and R convection 2 of the wall. We can add all of them to get a one final answer. And then we can just put that thing in. Now the advantage of this one is you will get an equation, Q equals, if I rub this one, we got Q equals to delta T over R total. Now, if I need to find the delta T, I can find out what is the change in temperature, Q times the R total, where R total the resistivity and Q is the rate of heat transfer. And the unit for that one, delta T, is going to be centigrade. That unit for this one is joules per second. Yeah. And that unit is watts. Yeah. So we can actually work it out from here.